The last section for college algebra, 13.3, geometric sequences and series. If you remember the arithmetic sequences and series, we had a recursive, we had an explicit, and we had a sum for a series. We're going to do the same thing for geometric. The recursive formula, it's similar to what the arithmetic is. You know the first term, let's call it B, and then every term after that, you take the first term and multiply by n minus 1 common ratios. So it's really that ratio to the n minus 1 power. For example, geometric is different than arithmetic because it doesn't have a common difference, it has a common ratio we call r. So let's start with 3, and let's call that common ratio, that's our first term. Common ratio, let's call that 2. So 3 times 2 is 6, times 2 is 12, times 2 is 24, times 2 is 48, etc., etc. So that's where this recursive can be very helpful, can help you create the first 5 terms easily. You need the first term and the common ratio somehow, and you just keep multiplying. So notice this, to find the common ratio, it's 6 divided by 3, that's 2. 12 divided by 6 is 2. 24 divided by 12 is 2. 48 divided by 24, and that's why they call it a common ratio. The arithmetic was a common difference. So r equals 2. A sub 1 is the 3. The explicit formula, you need the nth term is the first term, and I forgot, we're going to use g sub n for geometric. So it's the first term, g sub 1, times 1 minus r to the n over 1 minus r. That's for the series. Gosh. So let me give you the formula for the explicit formula. It's g sub 1 times r to the 1 minus n. So I'll take that again. G sub 1 times r to the n minus 1 power. Remember, for the arithmetic is a sub 1 plus n minus 1 common differences. This is g sub 1 times n minus 1 common ratios. So it's r to the n minus 1 power. For the series, geometric, the sum for the nth term is the first term, 1 minus r to the nth power over 1 minus r. That's what I was going to give you here. That was wrong. We can show you how to get this, except I guess we really don't need to. Let's show you how to use it a little bit, and then it'll be a little nicer. We might have understood at the time, maybe, that the arithmetic sequence and series never had an infinite series. And you might say, well, how can you ever add up an infinite number of things and get a finite sum? You can, possibly, for geometric. And they use S. I like S sub infinity, but they usually just use S. It is the first term over 1 minus r. But this only works if r is less than 1. Absolute value means really a negative 1 is less than r is less than 1. It's in between a negative 1 and 1. It's a fraction. And so you'll be adding just a little bit, and eventually you'll be adding almost nothing. And that's how it can be a finite sum. So if we take a few of these examples. So here's one. This is problem number 18 in this section. It says we're supposed to write the first four terms. That's the last thing, but we're going to do that first. Find the common ratio. And this is geometric, but we'll make sure of that. So if n is 1, we get 2 to the first over 3 to the 0, right? If n is 2, it's 2 squared over 3 to the first. If n is 3, it's 2 to the third over 3 squared. And if n is 4, it's 2 to the fourth over 3 cubed. So this is really 2 over 1. This is 4 over 3. This is 8 over 9. This is 16 over 27. Now, how do you find, if they were giving you this as the initial problem, how would you know this is geometric? You divide, right? 4/3 divided by 2 over 1, which is 4/3 times 1/2. 2 will go into this once and twice, and you get 2/3. Let's take these other two. 8/9 divided by 4/3, which is really 8/9 times 3/4. 4 will go once and here twice. 3 will go once and here 3 times. You get 2/3. If you take two consecutive elements of this sequence and you divide the right by the left, and you get the same answer all the time, that same ratio, that's what R is. So we've answered the last part of the question, and this is the second part of the question, and we've made sure that this is a geometric sequence. In this problem, we're supposed to determine whether this is an arithmetic sequence, a geometric sequence, or neither. If it's an arithmetic sequence, it has a common difference. 3 minus 1 is 2. 6 minus 3 is 3. And right away, we know it's not arithmetic. If it is a geometric, it has a common ratio. 3 divided by 1 is 3. 6 divided by 3 is 2. And right away, we know it's not geometric. Therefore, it is neither. There are others, like the Fibonacci sequence, but they want to know arithmetic, geometric, or neither. Okay, suppose we're supposed to find the fifth term and the nth term, and we know it's geometric, given the first term and the common ratio. Now, sometimes they'll use A's, I use G's sometimes for geometric, but it doesn't really matter. That's the first term of 6. So if we want the fifth term, A sub 5, for geometric, we need A sub 1 times R to the n minus 1 power, right? Or 5 minus 1 power. So A sub 5 is A sub 1, which is 6, times R, which is a negative 2 to the 4th power. This is 6. What is a negative 2 to the 4th? Well, because it's even, it'll be positive. And this is times 16. So it's 3696. Now, sometimes you don't even need to know what kind it is. If they want the 7th term of this sequence, this is a geometric sequence, but you can just keep on going. This is the first, the second, the third. The 4th is going to be 100.0. The 5th is going to be 1,000.0. The 6th is going to be 10,000.0. And And the 7th is 100,000.0. So even without recognizing that that's geometric, you can find that. Now we're given this sequence. We're supposed to find the sum. Since they're using an n here, it's really the nth partial sum. First of all, let's figure out. This 6/5 divided by 2 over 1 is 6/5 times 1/2. This goes once 3 times, so 3/5. How about the 18/25 divided by 6/5, which is 18/25 times 5/6. 5 will go once and 5 times. 3 will go once, and this is 18, so 3 times. We get 3/5. This is geometric. Now, our nth partial sum for geometric is g sub 1 times 1 minus r to the n over 1 minus r. So this will give us, because they do this in terms of n, we'll just have a formula for this particular one with some of these filled in. G sub 1 is 2. 1 minus r is that 3/5 to the nth power over 1 minus the 3/5. And we could take that further, but I'm running out of room. So that's one way, at least, of writing this thing. And we could simplify it a little bit more. Now, this is a series. And you know that because of the plus and minus signs there. You're adding things together. But we're supposed to find, see if we can find this infinite sum because it's got the dot, dot, dot. The only one we can find really is if this is geometric and if the common ratio is between a -1 and 1, not inclusive. So first of all, let's find the ratios here. This is a -3/4 divided by 1. Which is, of course, a -3/4. Okay, what about 9/16 divided by a -3/4, which is 9/16 times a -4/3. 3 going once and 3, 4 going once and 4, so we get a -3/4. Yes, it's geometric. And for a geometric infinite sum, first of all, this common ratio r is between a -1 and 1. So this will work. S sub infinity, or just S. It's the first term, 1 over 1 minus r. So it's easier to add up an infinite number of terms in this case. 1 over 1 minus -3/4, which is 1 over 1 plus 3/4. Well, 1 is 4/4, so 1 over 7/4. But when you take this, you want the reciprocal, 4/7. So if you add up an infinite number of these, you only get 4/7 as your possible sum. It converges to 4/7. That should do it. You should be able to do the rest of these.